when you guys were in algebra, you guys probably had a question similar to example 1, where it says, find two numbers whose sum is 20 and whose product is as large as possible. So when you guys had this question in algebra 1, you probably said something like two numbers, x plus y. Maybe you use a and b, I don't know. No, it's all good. X plus y, and you know that those two numbers have to add up to 20. And then you probably said, well, the product, the largest possible product. So let's see, product equals x times y, because I'm multiplying those two numbers. And then since you wanna be able to graph this to see how it's gonna look. So what I would use, a lot of times they call this a restrictive equation. The restrictive equation. So because we have a restriction, we know that that my output, well, okay, I guess I'll slow down here. Because we have a restriction here, so what do I mean by that? That y has to equal 20 minus x. So if I put this expression in here, I get this. P in terms of x is going to be x times 20 minus x. And because I took algebra 1 and algebra 2, I have an idea how this graph looks, because I can tell that I have a 0 at 0 and I have a 0 at 20. So because I know that, I know P of 0 is going to be 0, and I know P of 20 is going to be 0. Because I know that if I have a critical point, it must be a maximum. And this one's simple. You don't need calculus for this one. This one, you can just say, how does this graph look like if I were to plot P versus X, right? And I'm talking about this expression here. Well, I know I have a 0 at 0, and you have a 0 at 20. And because it's a parabola, I know that it's symmetric. And I didn't do a good job of drawing that symmetry there. And you can take a guess where my max is going to be at. The max is going to be at 10. And if I know that x is 10, I know that y is 10, because 20 minus 10 is 10. So the maximum possible product is 100. And when you were in algebra, maybe you graphed this graph, and then you just said, where's the maximum of that graph at? Well, the maximum of that graph is where this green dot is at. And that's it. But we're in calculus now, and we can figure this out without graphing. We could just figure it out by knowing the restriction, that I know that x has to be between 0 and 20. And because I know that P of 0 is 0 and P of 20 is 0, if I get a critical number, it must be my max. It must. So let's see, calculus route. Of course, like I said, we probably wouldn't do calculus on this one. So I'm going to distribute that x. So P of x is going to be 20x minus x squared. And then I'm just going to take a derivative, guys. P prime of x is going to be 20 minus 2x. I equal that to 0. You can already see that I'm getting a critical number here. 20 equals 2x. Divide by 2. And we get x equals 10. Now that I know that x equals 10, we're good. That's my critical number. So then I say, okay, what is P of 10? P of 10 is 100. So this must be my absolute largest possible product. And then I would probably write a statement. It says find two numbers whose sum is 20, whose product is the largest possible. The two numbers are 10 and 10, dot, dot, dot. Max product is 100. And that's it. So do we understand the idea of what we're about to do today, guys? Do you understand the idea?
I do.
Okay. Virtual class, do we understand the idea of what we're doing today? Okay. In case we don't know the idea, guys, what we're doing is we're finding max and mins, and you guys have been doing that for the longest time, but now we're using calculus to find for application problems. Right, Viacana? All right. So here we go. A rectangle. So the hardest part is just finding a model. That's the hardest part. A rectangle is to be inscribed under one arc of the sine curve. So here comes a little bit of pre-calc, not even that extreme. What is the largest area the rectangle can have, and what dimensions give that area? All right, so let's see. We might have to use Desmos. So here is my sine curve. I zoomed in. That's going to say y equals sine x. I know that at pi over 2, that's a 1. And it tells me that I have a rectangle inscribed. There's so many different rectangles I can have in here, guys. I can have a rectangle looking like this green one. Well, or I can have a rectangle looking like this blue one. It's not perfect, but it's supposed to be symmetric. It's supposed to be symmetric right on pi over 2. So what they want to know is, what are the dimensions? What's the biggest rectangle I can fit under that curve? Imagine that you can, this point here, this is a fixed point, and you can move that left or right all the way to pi over 2. You can just move it. And where do I put that point? Or I guess, yeah, I guess you can say, where do I put that point? Where do I put that point to make the biggest rectangle possible? Does that make sense to everyone? Or what's the biggest rectangle you can draw under this sine curve? And you know, the points up here, those have to be touching the curve because you want the biggest rectangle possible. So do we understand that? Okay, the hardest part is getting a model. So if I call this distance, let's see, if I call, let's use, does this color come out? No. Does this color come out? If I call this distance here an x value, then I know that this distance over here must also be, and I'm going to put it in quotes, must also be x. Yes or no?
Yes.
Perfect. So I know that the width of this rectangle is going to have to be pi minus 2x. Does everyone know how I got that? Well, what is this point right here in green? What is that point? The x value? Yeah, it's pi. So if that's pi and I want to know just this distance here in green, I'm going to go pi minus x, which is 2x. All right. Next, the height. Well, the height, I think, is the easier one. Did I spell height correctly? The height is the easier one. The height is dictated by this curve. See, the height is dictated by this curve. That curve is, oh, not everyone at the same time. That curve is sine x. So that means that x, I have a restriction for x, guys. That means that x must be, and you can make a case, x must be between 0 and pi over 2, and you can make a case about having the equal sign, because you're probably saying, Chavez, if x is 0, that means you have no rectangle, and you're right. And if x is pi over 2, that means you have no rectangle because it's you're real skinny. You're like literally on that black line. And you're right as well, again. But why do I say the restriction between 0 and pi over 2? Why do I put the equal sign there? Because I know that the area at 0 is 0. And I know that the area at pi over 2 is also 0. So if I find a critical number and I just have one value, I know that one value must be an absolute max. Does that make sense to everyone?
Can you repeat that again?
Yes. Because I know at 0, I don't have a rectangle. At 0, I just a flat line right on the horizontal, right on the x-axis. Because, you know, I haven't moved. You're just 0 at 0. If x is 0, I have a flat line right on the x-axis. I have no rectangle, so my area is 0. If my x value is pi over 2, that means you're right on this black line, here, and you just have a stick. And you have no rectangle again. It's just a stick. And it has no area again as well. Because at my two extreme values, I have no area, 0. If I get a critical number between 0 and pi over 2, I know for a fact that it must be an absolute max. It must. Does that make sense? Hello. Does that make sense or no? Okay, so here we go. The hardest part is creating a model. And we already figured it out. Look, you guys already figured it out right here. The area in terms of x is pi minus 2x times sine x. You're gonna have to use a calculator for this one because I can already see there's algebra with sinusoids. I'm gonna find my derivative. If you wanna distribute right now, that's fine. If you don't want to distribute to the very end, that's fine as well, because you're gonna have to use product rule regardless, one way or the other. Do you guys want me to distribute now or distribute later? Okay, distribute now. Pi sine x minus 2x sine x. You're gonna have to do product rule anyways. Here we go. I'm taking a derivative. Why am I taking a derivative? Because I'm trying to find a critical number that's going to make this statement true. That's going to give me the largest possible area of this rectangle. The derivative of pi sine x is pi cosine x minus, here's my bracket because I want to make sure that I get it right. First times derivative of the second plus second derivative of the first. What? Oh, yeah. No, you're good. I would have gotten it wrong. First times derivative of the second plus second times derivative of the first. I'm going to equal all this to 0. Finding critical. All right, here we go, guys. Distribute the negative. Pi cosine x minus 2x cosine x minus 2 sine x equals 0. And you might be able to solve this algebraically. No, you cannot. You have x with a wave. Nope, you can't solve this algebraically. You need a calculator. So I'm going to type this into Desmos. But remember, we're going to have to start eventually transforming back to calculators, guys. So I'm going to put that into Desmos, and I'm only going to check between 0 and pi over 2. So here we go. I'm going to open up Desmos. And right now I'm going to change the screen, guys. Let me just get Desmos in here and share my screen. Desmos. Oh, look, I already had Desmos earlier. All right, here we go. Math tools, graphing calculator. And I already forgot the equation. Can you guys hook me up? Y equals pi cosine x. What else did I have, Viacana? 2x cosine x. And then that's it. Okay. Go to your little thing here. What is that called again? A little wrench. And I'm going to put 0. And I'm going to put pi over 2 because that's all you care about. Just a value between 0 and pi over 2. And check it out. I want you to observe. I want you guys to observe. Is the derivative changing from positive to negative at that exact location that I'm crossing the x-axis? Yes, because it's changing from positive to negative. That is where I have a max. Because it's a closed interval, this is an absolute max. Cool? There it is, 0.7105. And I'm going to put that in here. So let me go back to And if you can put more digits, put more digits. This is true when x is 0.7105. If you can put more digits, put more digits. You guys ready? I'm going to put this in here. So I will get the width and the height, and then I'm going to find my area. So width, pi minus 2 times 0.7105. Don't round until the very end. Height equals sine of 0.7105. If you can use the register memory, use the register memory. And let's see what I get, guys. So I'm going to go to Desmos. Let's see, will it do it for me? How do I save this point? Is there a way? 0.705. I wonder if I put equals 0, will it give it to me? Nope. It's not a CAS. All right, I'll see how far it is, guys. I did it earlier here. So pi minus 2 pi minus 2 times 0.7105. 0.7105. Let's see how off it is. 1.7206. Don't outright the 59. Put 1.7206. 1.7206. And when you do the other one, you're going to get 0.6522. 6522. And then the area, when you're 0.7105, you can just multiply this width times height, and you're going to get 1.122 square units. You don't have to put unit square if you don't want to. This is my area. These are my dimensions. I'm going to use a calculator on the next one, guys. So we have to start transitioning to calculator usage. So I'm going to use the calculator on the next one. Let me see if I can type TI in there. TI. So I'm taking out the calculator real quick. I'm going to try to see if I can. Your subscription will expire in 6 days. Oh, that's nice. I'll buy one. Happy December? Oh yeah, it's December already. All right. Let's continue. Here we go. You guys ready? All right. To optimize something means to maximize or minimize some aspect of it. What is the size of the most profitable production run? What is the least expensive shape for an oil can? What is the stiffest rectangular beam we can put for a 12-inch log? We usually answer such questions by finding the greatest or smallest value of some function that we have used to model the situation. So, and this, of course, look, I put where I found it from, guys. That's not mine. I put quote unquote. And finding the model is the hardest part. Once you find the model, you can just use calculus to find a maximum or minimum. And we've been doing that for a long time. We've been finding max, we've been finding mins. So you find a model. If I want to maximize something, take a derivative, equal it to 0, find where it's the biggest. If I'm trying to minimize something, take a derivative, equal to 0, see where it's the smallest. If you have a closed interval, then that critical number has to be either your max or your min, depending on what the situation and the context of the question is. Does that make sense, guys? Yeah, you okay? You're not falling asleep on me, are you? Okay. You can get up, miss. That way, you don't fall asleep. All right, here we go. Example 3. An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? What are the resulting maximum volume? So there it is, guys. Of course, there's waste. The whatever you're cutting out is the waste part, right? But there it is, 20 by 25. And I'm cutting out the corners, X amount. And when I cut out the corners, X amount, here is how my box looks. Isn't that cool, the visual there? So the biggest volume. So how much do I have to cut from the edge to get the biggest volume? Or I guess you could also say, what is my X value to get the biggest volume possible? Before you start the equation, guys, look at X. X has a restriction. The smallest possible X value that you can use is 0. And I know you can make a case for Chavez. Why do you have it X less than or X greater than equal to 0 when you cannot be 0? You can make a case for that, guys. You can perfectly make a case for that. But there's a reason why I do it this way. And I'm going to tell you right now why. The biggest X can be is what? Look at the 20 minus 2X. What's the biggest X can be? Bless you. Oh. 10. The biggest X can be is 10. And if you're right at 10, yes, you can make a case. If you're right at 10, you do not have a box. The reason why I put an equal sign is because of this. My volume at 0 is 0, and my volume at 10 is also 0. So if I have a critical number between 0 and 10, that must be an absolute max. It must. Because my two extremes are zeros. Correct. Does that make sense, guys? Does that make sense? Okay, so here we go. The hardest part is getting a model. And this one's not, okay, you always ask yourself, what am I trying to maximize? What am I trying to minimize? What am I trying to maximize? The volume. So I need the volume expression. That's what I'm going to take a derivative of. I'm trying to maximize the volume, so I need the volume. Volume in terms of X is equal to X, yeah, length times width times height. It's a box. X times 20 minus X times 25 minus 2X. Everyone okay? If you want, you can do a triple product. Okay, what's up? Does someone have a question?
Is it supposed to be 20 minus 2x?
Oh yeah, it is. I would have gotten it wrong. Man, mistakes everywhere. Thank you. Thank you, miss. Thank you for letting me know about that. Now, if I were you guys, you can do a triple product rule right here if you wanted to, but I think it's easier to just make a polynomial. All right, let's do a polynomial. V of X equals, I'm gonna leave the X on the outside. I'm gonna multiply these two binomials first. 20 times 25, let's see, if I have 20 quarters, I have $5. So that must be 500. 20 times 2x, that's minus 40x. 2x times 25, that's another 50x. 2x times 2x, that's going to be a positive 4x squared because negative times a negative is a positive. I'm going to distribute the x, and I'm going to write the highest degree in the front because that's what we did in Algebra 2. X times all that shebang. So 4x cubed. Like I said, I'm writing the highest degree first. Then 40 and 50, that combines to me 90x. So I'm going to have minus 90x squared plus 500x. This is what I want to maximize. This is what I'm going to take a derivative of. So here we go. V prime of x equals 12x squared minus 180x plus 500. Equal that dude to 0. And then I start looking to see if it's factorable. That 500 is really messing things up for me. Let's see. I can factor out a 6. I can't factor out a 12. You can factor out a 4. But I'm not going to be able to get it in forms of factors, right? So I'm going to leave it like that. Is there an easy way to figure out what x is, guys? Did we learn something in Algebra 2? Yeah, no, we can complete the square, but is there another way? Starts with a Q. Quadratic formula, guys. A is 12, B is negative 180, C is 500. Quadratic formula. X equals opposite of B, so 180 plus minus square root. And then I guess you can write a negative 180 in there, put a square on it, but it doesn't matter, negative or not, it's going to be squared anyways. Minus 4 times 12 times 500 for AC, all over 2 times 12. I'm going to take my calculator and I'm going to plug those numbers in. So I'm going to show you guys my calculator. So we're going to stop with the decimals now because we got to start transitioning. So here is my calculator. Can everyone see my calculator? It's a pretty big calculator here. All right, I'm going to go ahead and start typing in. I'm going to push alpha y equals to get the fraction. So there's my little fraction. And I'm going to write, let's see, it was 180 plus square root. And if you want to be technical, you can put a negative 180 with a square on it. Put it in parentheses. Minus 4 times 12 times 500. Oh, really? See, don't you feel powerful, miss? You're learning so much every single day. 2 times 12. You are powerful, miss. Look what you made Wince do. Just with just a little bit of like, it was the voice. You sounded like scary. Put your feet down. So there it is. Ooh, already you should already be some red flags. Unless you're like totally lost, then you're like, I don't know what I'm looking for. It's greater than 10. It's definitely not that one. That one will give you a negative volume. So change that plus to a what? So I'm just going to push enter. You can just scroll up and push enter. And then I'm just going to change that plus to a minus. So left, 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 up. Come on, buddy. Minus. Enter. There it is. Do we know how to store it in a calculator? Okay, here's how you store it. It works the same with the TI Inspire. You see that number, 3.6811? There's a little button that says store. Next to, on mine, it's on 1. On the Inspire, I think it's in the upper right-hand side somewhere. It's in blue. I'll go over there right now, miss. Do you see? It's in blue or highlighted. You found it? So push store, and I like to go down the alphabet. So I'm going to store it into A. So there it is. So every time you push A, it's going to be that number. All right, let me go back, and don't worry, we're gonna use it in a little bit. So I'm gonna come back, and I'm gonna say that this gives me an answer, and what was it? 3.6811 centimeters. At least 3 digits. If you can put more, put more. So now they want my dimensions. Okay, so my dimensions are 3.6811 by 20 minus 2 times 3.6811, whatever that is. We're going to figure it out. And they're all centimeters, by 25 minus 2x cm. And we're going to figure out what those dimensions are in a little bit. Max volume is, and I'm going to figure out what that is in a little bit as well. So check it out, guys. I'm going to go back to my calculator. Here it is. Maybe I should have put the equation right off the bat, but I guess it doesn't matter. All right. What was my equation again? It was x times, so I'm going to go alpha A times 20 minus 2x. So I'm going to put 2 alpha A times, and then open parenthesis, and then 25 minus 2x, so 25 minus 2 alpha A. And I'm gonna push enter, and there it is. There's my maximum volume. 820.528. Now let's figure out the width and the height. And I guess I could have done 20 minus 2a. There is, if you want to call that width, you can call that width. And then 25 minus 2a. And if you want to call that, what's the other one? Length. There it is. So hook me up with those numbers in a little bit. 12.637 or 638, and then 17.638. I think I can remember them, but just in case. So let's go back. All right. What was my maximum volume? That I already forgot. 528 cubic centimeters. And the dimensions were dimensions. 3.6811 by, what was the 20 times minus 2.3 times whatever? By, centimeters. 17.637 centimeters. There it is, guys. Oh, the squares, these cuts, they're 3.6811 squared. Cool, right? Look, guys, look at all the calculus we did to figure out this problem for the maximum volume. So now if you want to figure out, do you think UPS and USPS did this? Yeah, they know all this math, guys. Let's, what's up?
The question is asking how large will the square be? Do we have to find the area of the square?
No, you can just tell me 3.6811 by 3.6811. Or cut out 3.6811 by 3.6811 of the little edges for maximum volume. That makes sense? Ooh, now you're gonna design a can, guys. Uh-oh. What is it? You're no. Well, because you got, okay, well, hold on, don't worry. Because there's two things going on here. You have been asked to design a 1 liter oil can shaped like a right circular cylinder. Oh man, the bottoms, let me write these better. There we go. What dimensions will use the least material? Okay, first we need to know area. You can say surface area, but then don't use two letters SA. I'm talking about surface area. Volume, yeah. Pi r squared h, yes. All right, area. This is what. Let's see. What dimensions will use the least material? Oh, I gave you guys the answer already. Darn it. I was gonna ask, what do I need to maximize? And I already wrote what I wanted to. What do I want to maximize or minimize? You want to maximize or minimize, in this case, minimize, because this is least material, the area, the surface area. So sorry, guys, that I gave you guys the answer already. That's what you're trying to minimize. We're not trying to maximize or minimize the volume because I already got the volume. What's the volume? 1 liter. Oh, Chavez, how are we going to go liters to centimeters? Oh, well, you all took chemistry, so we know the metric system. No, you took chemistry. So what dimensions will use the least material? We're talking about area, guys. So area, now this is a simple model because we have to count waste, and we haven't taken waste into account, like the top, like how you're going to open it, right? So let's see if we can just get a model real quick for area. The bottom is a circle. The top is a circle. They're both closed. Pi r squared. This is a simple model because we're not in engineering school. Yes, times 2. There's 2 of them. Plus, and now I need, yeah, it's a rectangle. Now I need the wall. So I need the circumference of the bottom times my height. So the circumference is 2 pi r, and then times your height, and there's your rectangle. Are we okay so far, guys?
Wait, what do you mean rectangle?
Yeah, if you were to cut one of the edges and you were to make this the wall into a flat, it would be a rectangle, right?
Yes.
Yeah. If you take a rectangle and you roll it up, it's a can. Yeah, like the label on a Coca-Cola bottle or something. Are we okay so far, guys?
Yes.
Okay. That's what I want to minimize. Oh, notice I can use as much material as I want. All right, let's use our chemistry, and it's simple chemistry, it's not even extreme. We're using this as a restriction. Volume equals pi r squared h, and it equals 1 liter. So before you graduate high school, there's a certain amount of common knowledge that we should know. How much is 1 liter in cubic centimeters? Oh man, guys, 1,000. 1,000. Guys, before you guys go to your university, if you're going into the medical field or engineering field, please make sure you brush up on your metric system, guys. Friendly, guys. Friendly competition. Viacana is looking at me with hateful eyes. All right, please put a side note somewhere. 1 liter is equal to 1,000 cubic centimeters. Please know that. You should also know Avogadro's number and the speed of light and stuff like that. What's a kilogram? Kilo hectodeca base, this is centimilli. So please know like the basic metric system, guys. So there it is. We're gonna use this. This is your restriction equation. So we're gonna use that. And since I wanna take a derivative, I can take a derivative with everything in terms of h or everything in terms of r. I can leave the r and the h there, but it's easier if I take a derivative with one variable and one variable only. So I could either solve for h or solve for r. Which one looks like it's easier to solve for volume here? Yeah, it looks like it's easier to solve for h. So h is equal to 1,000, remember it's cubic centimeters, divided by pi r squared. I'm going to take this number and I'm going to insert it into that h right there. So now I have area in terms of r is equal to 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Are we okay so far?
Yes.
Okay, we got 2 yeses. All right, everyone tell me yes. Evangelista, Dinan?
This feels like related rates.
It's not related rates, miss.
No, I know, but like coming up with an equation and like it feels like it.
It's all very similar. Let's see, 2 times 1,000, that's gonna be 2,000. The pi's cancels out. One of the r's cancel out, so you have 2,000 over r. Get up to there. Langford, you doing okay?
Yes, sir.
Okay. This is what I want to minimize. This is what I'm going to take a derivative of. But we got an issue, a small issue. No, there is. It's a very small issue. Am I restricted with how much material I can use? I can use as much as I want. So here's the issue. How do I know that that critical number is a minimum? Since R isn't a closed interval, how do we know that when a prime of R equals 0, comma, that this specific R value is a minimum? Question mark. I'm going to read it again, guys. Since R isn't a closed interval, how do we know that when A prime of R equals 0, that this specific R value is the minimum? Do we have any tools in our bags that can tell us how we can figure this out? No, well, okay, yeah, calculator. But is there another? Yeah, we can check if the derivative changes from what, negative to positive at that R value. Yeah, that is one way. Is there another way? Okay, well, yeah, for R prime, where it changes from negative to positive, is there any other way? If you have a max, so concavity. If f prime prime, no, we need it to be positive because we want a minimum, right? If I have a function that is always concave up, and I have a critical number at 0, I have a critical number where the derivative is 0, then that critical number must be an absolute minimum because you're always concave up in the entire domain. And that's the only place where you have a horizontal tangent. Does that understand? Like a parabola. Okay, so here we go. I'm going to have to take two derivatives. The first derivative to find critical number, the second derivative to prove that it's always either concave up or concave down. So here we go, A prime. So the derivative here is 4 pi r minus 2000 over r squared. Is everyone okay with how we got that? I'm going to equal that to 0. 4 pi r equals 2000 over r squared. I'm just solving for r, guys. That's all I'm doing. Times r, I get 4 pi r cubed equals 2000. I'm going to divide by 4 pi. R cubed equals 4 times 5 is 20. So I think that's 500. Check my math, guys. I make mistakes all the time. 500 over pi. Hmm. 500 over pi. I see 500 over pi. I see two of them there. Okay. And why did I put an equal sign? Oh, what is this here? That's my derivative. I set it equal to 0. Okay. I want r. I'm going to call r the cube root of 500 over pi. And we can simplify that, but I'm going to leave it like that. And I do see, it looks like r equals 2h or something like that. But that's fine. Because I'm looking at, see how you have 1000 over pi? And I have 500 over pi. So two of those goes into, yeah, don't worry about it. I may be wrong. Are we still okay, guys? All right. I want to make sure that that is an absolute min. That's what I want. So I'm going to take another derivative from right here. From right here. A prime prime of r equals 4 pi. Negative times the negative is a plus. And then what's 2 times 2000? 4000 over r cubed. Notice there's a plus. Oh, I love this. Greater than 0 always, since r is always greater than 0. So this tells me that A is always concave up. So I'm going to write since A of R is always concave up, A prime of R yielded an R value of R equals cube root. That's a cube root, guys, not square root. 500 over pi, which must be an R value that uses the absolute least amount of surface area. Guys, I hope that when you guys go shopping, you start seeing calculus in the design of cans. Why are all cans designed the same way? Why do all Coke bottles, Sprite, Dr. Pepper, why do all manufacturers have cans that way? Because it uses the least amount of surface area for the amount of liquid that it contains. If not, they would use, like, do you ever see water bottles that say uses less plastic, but same volume? They're using calculus there, guys. They're finding the absolute minimum. Sometimes, yeah. Well, if they use less plastic, that saves them money. So I don't know if they necessarily care about the environment, but we know that they care about money. Why the what? It's not negative. Oh, I'm confused.
Okay, so we jumped from that, the second derivative equation, to the answer, but I think it might be.
Okay, yeah, I haven't done yet. All right, guys. In case you're wondering why this R value is the absolute minimum, the function, I don't know exactly how it looks like, guys, because I haven't graphed it, but I know it has to look something like similar to this. Let's see, it probably looks something like this. And then here's my critical number, and then something like that. Notice that it's always concave up, and that has to be the one that's going to give you the smallest amount of area. If I call this area, and I call this R. Does that make sense, guys? And because I can use as much as I want, you have to do the second derivative. And notice I have a horizontal tangent there at that moment. So my derivative is 0. And you can see that it's concave up all the time. So that has to be an absolute min. Yes.
Second derivative are negative,
Then we would, yeah, we don't have a solution. Depending on the context of the question, then that means that it has an absolute max or whatever. If I would have had a, you know what I mean? But in the way this question is worded, like these type of questions, you're always going to have minimums. These don't have maximums. This one, as you can see. Cool. All right. Look at all this beautiful math, guys. Example 5. This one's coming from UH, so we're giving them credit. Find the coordinates of the points on the curve y equals square root of x plus 4 that are closest to the point 7, 0. Ooh, I like it. I like it, guys. No, there's more, but I just got lazy and typed in 3. First, let's start by graphing. Y equals square root of x plus 4 looks something like this. -4. And the point, this is not to scale, so don't judge me here. 7 is like 7 zeros, like somewhere there. And they want, what is the smallest distance? Which one of those lines is smallest? Find the coordinates. So they want a coordinate. So which one of those green dots is smallest? And I guess since it keeps going all the way, this would have entered like that, see? Yeah, you can come in, sir. The smallest distance between 7, 0 and the curve.
So these are, you can put the sum off between the staples.
Okay.
That's what you want to do with that.
Correct. Okay,
And then
thank
we'll
you.
figure out how we're gonna wash them.
Cool. Mhm. Did we understand the question, guys? Maybe. We're gonna find out right now. All right, virtual class, do we understand the question?
Yes.
Okay. All right, so here we go. Do we know the distance formula? It's similar to Pythagorean theorem. They're all related. They're brother and sister. Change on x squared plus change on y squared, and it's the square root of that. Now this is what I want to minimize. So this is what I'm going to take a derivative. Now I put this one in here because this is the hardest question that there is on this quiz here. And we're not ready to take the quiz, by the way. So notice that you have an actual activity where you're going to be doing some stuff by hand. All right, so here, be with me here real quick. If I want to take this derivative, it's going to be a killer chain rule. Why? Because notice you have a square root, and then notice you have squares here. So it's going to be chain rule and then chain rule again. You guys see that? So to make life easier for you, and this is a trick that everyone uses, even the top professors, so we're not cheating you here. This is what you want to maximize or minimize. So what does it matter about that square root? Like, what does it matter? If I want to minimize it, I can just take that square root away, and the smaller that this expression on the inside is, the smaller the argument is, the smaller the square root's going to be. Does that make sense? Odinas, does that make sense? Yeah, it feels like a cheat, like a big time cheat, right? But trust me, it's going to work. So I'm going to substitute. We're going to do a cheat. We're going to pull a cheat. So I'm going to write the word cheat, and I'm going to say, this is what I want to minimize. That way we don't have to do crazy chain rule. Cool or not cool? All right. Because all I care about is finding a critical point. So when I take a derivative, it doesn't matter if there's a square root or not. When I take a derivative and I'm finding a min or a max, you still have to equal to 0. So because I want the argument on the inside to be the smallest possible, who cares about that square root? I am going to equal to 0. Oh, you have to be on the curve. You know what I mean? You have to be on the curve. All right. So here's what I know, guys. I have a point. The point is 7, 0. And then the other point that we do not know, it has to be on the curve. So that means it's some x. And don't say y. What am I going to say? Square root of x plus 4. Because that's your y value. Are we okay so far? So here we go. I'm writing the expression that I want to minimize, the change in x. So I know that one point is 7, 0. So I'm going to write, let's see, I'm going to write x minus 7 squared plus square root of x plus 4 minus 0 squared. And yes, I realize that the distance formula is the square root of that, but it's going to be the same thing. We just took out the square root so we can minimize this. Like if we can minimize the argument, you find the minimal. We still okay? All right. I'm going to go ahead and do the algebra first, guys. D equals x minus 7 squared, x squared minus 14x plus 49 plus the square root of that squared, x plus 4. Now look, it's beautiful now. D in terms of x is equal to x squared minus 13x plus 53. Let me know if I made any mistakes. I don't see any so far. This is what I'm going to take a derivative of. D prime of x equals 2x minus 13. Equal that to 0. 2x equals 13. X equals 13 over 2. You were right, Viacana. 13 divided by 2. Oh, no, you were almost right. And not directly above it, but very close. All right. Delete anything that does not have a 13 over 2. How did they get the square root of 42 over 2, guys? Yes. Insert this into y equals the square root of x plus 4. Whew. We okay? All right. All right, guys. That was the last one.